Energy 101. We've been talking about the natural resources that we have to drive our energy system, and we've been talking essentially about fossil fuels, coal, natural gas, oil, and let's look at some renewables like solar. Today we're going to want to look at solar energy resources. It's a new ball game when you start talking about solar and wind as renewable resources, because with coal and oil and gas and that kind of fossil fuel, it's very convenient. You can just fire up your plant, whatever you're fueling with those fuels, and crank them up and run them wide open. You control the throttle, so to speak. You can run them wide open. You can let them idle. You can, just like your car, and you have total control. It's what we call dispatchable in the electric utility industry. But whether it's your home furnace, you can turn it up and down and keep your home just the right temperature. But when you have solar and wind, the sun doesn't shine so brightly all the time, and the wind doesn't blow strongly all the time. So we have to make sure that the way we use these renewable energy systems can accommodate that up and down resource, and that it comes and goes. In the case of solar, of course, the sun only shines on the average of 12 hours a day, and doesn't shine any at night, so that's the problem right there. And then you have clouds. But how much solar energy is there available? We're looking at it as a resource here that is striking the earth, that we can figure out, so we can figure out how much there is, and how then we can determine how to use that energy that's striking the earth. But there's about 300 at noon on a clear day. So if you got no clouds, it's a nice, bright, shiny day. And at noon, and the reason it has to be at noon, because that's when the distance that the sun has to travel through the Earth's atmosphere is the shortest. You can imagine when it's over at an angle, early morning or late, it's shining at an angle on you through a longer distance of atmospheric gases, and that attenuates the sun somewhat. So it's always brightest at noon, assuming there are no clouds, because that's when the path length through the atmosphere is the shortest. So at noon and on a clear day with no clouds and low water moisture, if you look directly at the sun and point a surface directly, that's 1 square foot, point it directly at the surface, so that it's perpendicular to the surface, to the sun rays, you'll get about 300 BTUs per hour falling on that 1 square foot. Or if in metric units, it's 1 kilowatt per square meter. And there are about 10 square feet in a square meter. So there's about 1/10 of a kilowatt per square foot, if you want, in kilowatt units, or 300 BTUs per hour falling on 1 square foot. So that's the best you can do at noon on a clear day. But now it's decreased by clouds and the angles from early morning to late afternoon. So life gets complicated when we're trying to calculate even how much solar energy is available as a resource. But the good thing is it's free. We don't have to pay anybody for it, like we do fossil fuels in particular. Well, photovoltaics has really come onto the forefront with the dropping cost in the last couple of years. And this is just showing one installation on a house roof that's fairly typical. On a house, when I say typical, it's a typical good one. The house was obviously, and looks like, designed for the collectors. The house was oriented so it's facing south, and the angle of the roof was such that it collects the most energy, sunlight, over a year. So the best angle to tilt, because the sun, and depending on time of year, is either high in the sky or low in the southerly direction if you're in the northern hemisphere. But for the best annual solar resource falling on your collectors, you want to face the collectors due south, and you want to tilt them up from the horizontal the number of degrees equal to your latitude. In Atlanta, where I am, our latitude is 35 degrees. So to get the most solar energy falling on a flat, fixed surface, we tilt the collectors in the southerly direction 35 degrees. Of course, on the equator, a horizontal collector will collect the most sunlight over a year, and this is on an annual basis. If you're trying to optimize it for January and you don't care about the summertime, then the angles are different. If you want it optimized in July, then the angles are different. But over the annual average, the latitude, and there's geometry that shows that, the best geometry is to have it tilted from the horizontals in the southerly direction. And of course, the other limitation, you can't have any trees. Here in Atlanta, most of our residential areas, we're blessed with a lot of trees in one way, but then you get a lot of shading. And so where you can use solar energy depends on the site and the location and the orientation of the house. Another way we utilize solar energy is what we call solar power tower. There are several ways. I'm just pointing out the two big ones that we're talking about now that's expanding commercially and fairly rapidly. And in this case, you've got thousands of mirrors that you see down there. This is made from an airplane looking down on this circle that's probably a quarter to half a mile in diameter. So it's a large installation. It produces electricity. And of course, the photovoltaic cells produce electricity. The sun shines directly on them, and the solid state device has wires running to it, produces electricity from that. In this case, the sun is reflected by these mirrors, that each one of these little dots are mirrors on the surface of the earth, and they track. They have two-axis tracking, we call it. You can orient them in any direction you want to. So a computer program makes those mirrors track, so the sunlight falling on their mirror is reflected off of that mirror onto the top of this tower. And on the top of this tower, there's a boiler, a steam boiler. Just like in a steam power plant fueled by coal, there's a boiler, and the hot fire boils the steam. In this case, all the sunlight that is reflected onto this boiler heats the boiler up for very high temperatures and boils the steam. So this is one that you've seen built, several of them are being built right now, as a matter of fact, out in California, the Mojave Desert, and Arizona, and those places. The first ones were built back in the 80s. Technology has been around for a while. So for large-scale solar, this is a pretty cost-effective way to produce electric power. But again, it produces electric power from a conventional steam power plant cycle, but it's using the sun to heat up and boil the steam that's reflected from these thousands of mirrors, rather than a fire that's burning fossil fuels. So how can we calculate how much energy strikes the solar collector surface? Well, as I mentioned, it varies by day of the year, because that's dependent on where the sun is in the sky. And but let's look at the annual average energy per day falling on a fixed collector tilted south. Now, this includes weather situations, cloudy days, rainy days, night, of course, and so it's the average, and it varies by geographical location. And it also varies by your solar collector orientation and your tracking method. If you have two-axis tracking, where it's always looking directly at the sun, well, that's the best. If you have a fixed plate tilted south at the latitude, which we've just been discussing, that's another option. Or sometimes you may only have a flat horizontal surface, or you want to put them on the side of a building and it's only have vertical surfaces. In our energy buildings, the Carbon Neutral Energy Solutions building that we just built here at Georgia Tech, it has some photovoltaic collectors on a horizontal awning surface, as well as on the vertical surface, as well as on the roof tilted south. So it's got collectors mounted on one new building with 3 different orientations. But so how much energy, solar energy, falls on a square foot or a square meter on an average day throughout the year can be calculated, and it depends on where you are in the U.S. You can see here that Over here in Arizona, New Mexico, you get the maximum solar energy falling, and over in Florida and in the Northwest, you get less solar energy falling, and so that's a excuse me, yeah, and there's a scale here. The maximum we get is about 7 kilowatt hours per day on average for the year. 7 kilowatt hours per year out here in Arizona, California, New Mexico. And when you move to the lighter yellow areas, then it goes down, and the minimum in the U.S., like up here in the north, you get about 4. So there's almost a factor of 2 difference in the amount of solar energy falling on these collectors, depending on where you are in the U.S. And notice it says at the top, this is annual in the upper right-hand corner, so that's the annual average. It's also the flat plate tilted south at the latitude, so it's not tracking, it's fixed, but it's as majority of the collectors and the solar system installations are mounted in exactly this manner, tilted to the south at the latitude, and they're fixed. Well, how might we calculate it? We can actually calculate this for your location, and by going to a U.S. Department of Energy National Renewable Energy Laboratory called NREL out in Golden, Colorado, and it's a laboratory of the U.S. Department of Energy, and they got an interactive online map. So let's go to this interactive online map. The web address is, as you see in the blue here, HTTP. It's a long one. Hopefully you can click on it and it'll take you there. You can copy and paste it into your browser. So I have my browser up here at that location, and this is the first page, U.S. Solar Radiation Resource Map. So you probably want to stop your video and pull this page up at this point and then come back. And we'll walk through how to use this to calculate whatever situation and orientation and geographical location you might be interested in. The first thing you can do is you can select the data type. You can select average, which is noted there right now. You can select the minimum, or you can select the maximum for the day. You know, maximum for the day or minimum for the day on the average. You can look at the selected by the month. You can pick one month, January or February through December, or you can pick the annual average. You notice for the chart that I had up in the previous slide, I had selected, as I mentioned to you, the average, annual average, and I picked, and I wanted to see the annual and not the minimum or maximum for a particular day. And now you can select the orientations. They have a lot of orientations, more than I mentioned to you. You have single axis tracking concentrator. This is just tracking one axis rather than 2 axes, which of course is cheaper, but is more than 2 axes, but it's more expensive than a fixed collector. And so there are several single axis tracking options here, and you got 2 axis tracking flat plate right here that always will make the collector look at the sun, but of course it's got to be mounted on a tracking device. It's got electric motors that's controlled by computers that always keeps it looking flat, straight at the sun. And you can do the one that most installations are using, a flat plate tilted south at the latitude. And that's the one that I had selected to generate the map that I just showed you before. You can pick the horizontal flat plate down here. Horizontal flat plate, that if you've got a horizontal surface and that's all you got and it's the cheapest way to install them, then you can look and see the penalty for mounting them horizontally versus tilting them south at the latitude angle. Of course, if you're at the equator, the horizontal is also the optimum. You can look at the south-facing vertical plate, flat plate on the south-facing wall. North-south axis tracking, they got a lot of options here. I won't bother to go through them. But if you look at the horizontal flat plate, I'll pick something different on this one than the map that I showed you earlier. And you go down here then and you just make those 3 selections and click View Map. And now you get this map, and you get a, as you see there, and you get the down here, you get the kilowatt hours per day. It runs from 10 to 14 kilowatt hours per square meter per day, the color, which none of it's on there, all the way down to the darker blue, which is 0 to 2. And of course, again, the southwest, which is where you see a lot of installations, is the best. And then as you move north in this situation, you're getting further away from the equator where the horizontal is optimum, and you collect less and less energy, or less solar energy strikes the surface. So that's a nice interactive website, so you can look at your situation and look at any kind of tracking option or mounting option that you might be interested in. Thank you.